Let's revise the basic concepts from remainder and factor theorem. So remainder and factor theorem is used when we are dividing polynomials. So we know that polynomials are expressions with some variable, algebraic expressions. Now let's say that we have the variable x, and let's say that we have a polynomial in x which is denoted by the notation f of x, f bracket x, and the degree is greater than or equal to 2. Degree is the highest exponent on the variable in the expression. And we have another polynomial g of x with the degree 1, and that's known as a linear polynomial. Now the reason why we are using this notation is that f of x we can consider a polynomial function. Function means that we have some relation between some variables. For example, if I say that there is a polynomial like x square plus 1, if I look at the variable and then if I try to substitute some values in the variable, the entire expression will result in some value. So we will have a value of the variable and the value of the resulting expression. So that's why if I consider this as f of x, if I substitute x equal to 0, then the value of this entire expression will be 0 square plus 1, which is 1. So I will say that f when x equal to 0, the value is 1. So this notation is easier when we are trying to substitute values in a polynomial, and we are also looking at what's the resulting value of the entire polynomial. Right. Now let's go back to the original problem where we are trying to divide two polynomials. Let's say we are dividing f of x with g of x, and I have mentioned that the degrees of the polynomials are like this. The g of x is a linear polynomial. Now whenever we are doing division, we have a dividend, divisor, quotient and remainder. This is true for whether we are dividing numbers or whether we are dividing polynomials. So the relation between these things is always that the dividend is equal to divisor multiplied by quotient plus remainder. For example, if I was dividing numbers like 12 divided by 5, then 12 is my dividend, 5 is my divisor. And if you remember the long division, then I will get 5 times 2 is 10 and the remainder is 2. So I will say that the dividend 12 is equal to the divisor 5 multiplied by the quotient 2 plus the remainder 2. So this is true always. Now for the situation of division of polynomials, I will say that my dividend f of x will be equal to divisor g of x multiplied by some quotient q of x and some remainder r of x. The quotient and remainder we can also assume are some polynomials. Now also one thing to notice is that the divisor here we are taking a linear polynomial, so degree 1, and the remainder will always have a degree less than the divisor. So the remainder will have degree less than 1, that means degree 0, and a polynomial with degree 0 is just a constant number. So I can also just write r instead of r of x because it's just a constant number. Okay. Now here we have to find out for what value of the variable the divisor polynomial will be equal to 0. So for example, if I choose x equal to a and a is some real number for which the divisor g of a will become 0, then for that same value of x, if I substitute in the dividend, I will get the expression f of a. This is the value of the dividend when x is equal to a, and that will be equal to 0 multiplied by whatever quotient we were expecting plus the constant remainder. Now 0 multiplied by anything is 0, so I will say that f of a will be exactly equal to the remainder r. So in conclusion, whenever we are dividing polynomials, if I am able to find out some value of x for which the divisor is 0, and that same value of x, if I am substituting in the dividend, that value of the dividend polynomial will be equal to the remainder of the division. So we are able to find out the remainder even without actually doing long division of polynomials. This is one way to find the remainder if we need to find it. So as an example, here I have written that let's say I am dividing x square minus 5x plus 8 with x minus 2. So x minus 2 is my divisor, and if I find x equal to 2 will give the value of the divisor 0. Then the same value of x, if I substitute in the dividend, I will get this expression 2 square minus 5 into 2 plus 8, and if I evaluate that further, I will get the value 2. So if I had the question that what is the remainder when I am dividing x square minus 5x plus 8 with x minus 2, then the remainder will be equal to 2. So without even doing actual division, I am able to find out what's the remainder. Now suppose in that entire process, f of x divided by g of x, the remainder that we get is actually equal to 0, then we can conclude that the divisor g of x is actually a factor of the dividend f of x. For example, if I do a division like 10 divided by 5, and if I do the division, 5 times 2 is 10, so I see that the remainder is 0. So when I see the remainder is 0, I will conclude that 5 is a factor of 10, right? So in case of polynomials, let's take the example of x square minus 7x plus 10, I am dividing with x minus 2. So if I look at the value of x equal to 2, the divisor becomes 0. So the same value x equal to 2, if I substitute in the dividend and I evaluate that expression, I am getting the result 0. So that means the remainder in this situation after doing the division is 0. That means x minus 2 has to be a factor of the dividend x square minus 7x plus 10. Then another important application of remainder and factor theorem is that we can apply this theorem to completely factorize some higher order polynomials. Specifically here we are taking cubic polynomials, that means it has degree 3. Now let's say that my cubic polynomial is f of x. Now if I do trial and error, I will just take some values of x, and if I find some value of x like x equal to a, for which the entire expression, the entire cubic polynomial becomes 0, then my conclusion will be that x minus a is a factor of the cubic polynomial f of x. So the values that we might be taking is some integers like 1, minus 1, 2, minus 2, like that. So if I am able to find some value for x for which the entire cubic polynomial is equal to 0, then I will conclude x minus a is a factor of f of x. The reason being that if I substitute x equal to a in the linear polynomial x minus a, then this becomes 0. So if I am looking at fx, the cubic polynomial, divided by x minus a, then this divisor x minus a is equal to 0, and for that same value of x, if I am substituting in my dividend, which is f of x, and that is equal to 0, it tells me that the divisions gives me the remainder 0. So hence x minus a is definitely a factor of the dividend f of x. Now I am able to find out one linear factor of the cubic polynomial, but the cubic polynomial can have up to 3 linear factors. So I have to still find out the remaining factors. How can I do that? I will do a long division polynomial fx divided by x minus a. Now since x minus a is a factor of fx, the remainder will be 0, and I will be able to find out what's the quotient exactly, and the quotient we are expecting to be a quadratic polynomial. It will be a polynomial with degree 2. Now fx will be equal to the linear factor x minus a multiplied by this quadratic polynomial, and we know that we can split the middle term to factorize the quadratic polynomial, and hence we will be able to factorize the cubic polynomial into 3 linear polynomials. As an example, I have taken the cubic polynomial x cube minus xx square plus 3x plus 10, and if you plug in some values of x like x equal to 1, x equal to minus 1, x equal to 2, for some value of x you might find that the entire polynomial result will be 0. Suppose here I am taking x equal to minus 1 and I am substituting in this cubic polynomial, the expression becomes 0. So f of minus 1, let's say that the cubic polynomial we are considering as f of x, then f of minus 1 will result in 0. So I will conclude that x plus 1 is a factor of fx, because for x equal to minus 1, x plus 1 will be equal to 0, and then if I am dividing the cubic polynomial with x plus 1, the remainder is 0. So I will conclude that x plus 1 is a factor of the cubic polynomial f of x. And then I am doing a long division polynomial where the divisor is x plus 1 and the cubic polynomial is my dividend. So through the long division process, obviously my remainder as expected is 0, and the quotient is x square minus 7x plus 10. So my conclusion will be that the cubic polynomial f of x is actually x plus 1, the divisor, multiplied by the quotient x square minus 7x plus 10. So the quotient is a quadratic polynomial, and we can split the middle term to say that the cubic polynomial finally when factorized is actually product of these 3 linear factors, x plus 1 multiplied by x minus 5 multiplied by x minus 2.